Okay, in this video I want to pick up where we left off in talking about variability. And we again define variability as the quantitative measure or of the differences between scores, and it also will describe the degree to which the scores are spread out or clustered. So we had looked at the measure of center called median paired with its measure of spread, interquartile range, sometimes just the range. And these are very useful tools for measuring center and spread if the data is skewed or if there are extreme values. Okay. A lot of times though in this course we're going to kind of idealize things and look at data sets that are very symmetric and don't have any sort of extreme values. In that case, we're going to be looking at the mean as our measure of center and what we're going to call the variance as our measure of spread. So kind of subsequently we need to talk a little bit about the mean and the variance in terms of standard in terms of sample and population. The mean, the symbol we give the mean when it's the population. The parameter we give it this Greek letter mu, and it's the lowercase m in Greek. Okay, if it's the sample, we give it the capital M. Okay, sometimes we give it this X with a line over the top called X bar. Okay, depending on the context. So outside, if you're looking up articles online and trying to find some help or something, you might see this X with a bar over it. But standard for APA, we're going to use the capital M for the sample mean. We're going to define variance in just a moment, and variance would be the measure of spread based on the mean. But I just wanted to highlight these two differences. And so from time to time I'll use mu if I'm talking about population. I'll use a capital M if I'm talking about the sample mean. Okay, so let's switch colors to something like green and go to a new page. So if we wanted to look at measure of spread based on mu. So remember that we can define mu as the sum of our x's, which are the observations, divided by the sample, the population size, and we define capital M as again the sum of the x's, but now we're going to divide by the sample size. Okay, so in either case we're looking at the sum of observations divided by the number we had. When we want to construct a measure of spread based on this, we want to also incorporate that idea of adding something up, adding a list of observations and dividing by that number of observations. When we look at the variance, let's just use the word variance, we're going to define variance as the average squared distance each observation is from the mean. Okay, so we're going to look at how far away each observation is from the mean. We're going to square that and we're going to add them up and divide by the number. That'll give us the average, and that's how we're going to define variance. Okay, so real quick, let's think about this. If I have a set of observations x, I can compute, so this is my list of observations. I can compute my mean, mu, so this is the mean. Okay, and I want to know how far away each observation is from the mean, right? So if I can look at how far on average each observation is away from the mean, that'll give me a sense of the spread of the data set. So what we can do is look at what we call the deviation, which is the difference between each observation and the mean. This is called the deviation. Okay, and if we look at each deviation, we're going to find that some are below the mean and some observations are below the mean, some are above the mean. So in other words, some deviations are going to be negative, some are going to be positive. And what we'll discover is that if we added up all of the deviations directly, they always add to 0, which is not very helpful, but it makes sense if the mean is the center of the scores in terms of the value. If I add them all up, add up all the differences from the mean of course it'll add to 0 because we built the mean using the same technique. So it's essentially undoing everything we just did to compute the mean. So what we're going to do is actually look at the squared deviation, and that's where this part comes in. We're going to look at the squared deviation, and that'll tell us how far away each observation is squared, and then at some point to return it back we're going to square root. Okay, so let's take a look at an example first. So let's say that we had a data set, a list of scores. X is equal to 1, 2, 2, 4, 4, and 5. What we want to do is look at the histogram of this first, just to see what we're dealing with, and then make a decision if we should use the median or the mean. If it's symmetric, we should use the mean. If it's not symmetric, then we should use the median. Okay, so let's do a quick sketch of a histogram. Let's see how well I can do here. Not very well. 1, 2. 1, 2, 3, 4. Whoops, 5, 6. All right. My artistic skills are lacking. So we have frequency of 1, 1. We have the frequency of 2, 2s. No 3s. We have 2 4s all the way up there. And we have 1 5. Hey, so that's a nice looking data set. It happens to be symmetric, but it is bimodal. So there's 2 peaks in it. So let's see, if we put a continuous approximation in there, we do something like this. Hit one peak, come down, 0, hit the other peak, come back down. According to my yellow sketch, it doesn't look symmetric, but it is symmetric. We have even distribution of both on both sides, so both modes. That's good. We can verify this by showing that the mean is equal to the median. Okay, but just visualizing it, we see, yeah, it's pretty symmetric, and we're expecting the mean to be somewhere, let's do it in green, somewhere in here. Okay, halfway in between, so maybe around the value 3. That's where we're expecting to find the mean. Okay, so let's see, let's compute the mean. We need to have the sum of the scores. So 1 plus 2 plus 2 plus 4 plus 4 plus 5. Okay, so that's all together, let's see, 6, 6, 12, 13, 15, 18. Okay, and so then the mean, mu, is equal to the sum of the scores divided by the total number, so that's 18 divided by 6, so that's 3. Hey, we see that already, so here's our mean right there at 3. Let's see, what about the median, just to verify that it is symmetric. Again, the median is going to be the middle observation if they're lined up. So, okay, there's 6 scores. If we add 6 and 1, we get 7. So we're looking for the 3.5 value. So that's occurring between the third and the fourth. So the average here is 3. Hey, great. So the mean equals the median, and we have a symmetric data set. So that's great news for us. We would like to continue using the mean and the variance because it's a much more computationally rich measure. Okay, it gives us a lot more information when we compute it. Alright, so let's think about this. If we want to calculate the variance, we have to start with our list of scores. So let's do this in green. Here's our x. Okay, we're going to make a little table here. 1, 2, 2, 4, 4, and 5. And let's look at each deviation minus the mean. Okay, so we're using the formula laid out in the book for first for the variance here. So 1 minus 3 gives us negative 2, 2 minus 3, negative 1, negative 1, 4 minus 3, 1, 1, and 5 minus 3, 2. Notice that the sum of these deviations is 0. Okay, that's always true. If you look at just the deviations, the sum of them will always be 0, and that makes sense because the mean is the center value, and if we're looking for the deviations, the sum of the deviations, that's like essentially like we compute the mean by looking at all the values, and then if we subtract each value, subtract the mean from each value, we're basically undoing that. Okay, so it's like adding the opposite to each one, and then we add them up and you get 0. Okay, so that means we need to look at the squares of each deviation. And the reason for that is when you square a number, it's always positive. And when you square root a number, it's again always positive. So we look at negative 2 squared, which is 4, 1, 1, 1, 1, 4. And now when we look at the sum of the squares, the square deviation, we get 4 plus 1 plus 1 plus 1 plus 1 plus 4. So that's 8, 9, 10, 11, 12. Okay, not 0, which is really good. So we define the variance. So variance, so in our case, it's going to be the sum of x minus mu squared over the population. So in other words, again, we're finding the average, right? So if we look back up here at the mean, this is taking the sum of observations and dividing by the number we have. Here we're taking the sum of a particular style of observation that we've transformed, and then again dividing by the number we have. So that's why the variance is said to be the mean of the squared deviations, okay? So it really is the average. So here we have 12 over 6, so 2. All right. So if we think about this, let's maybe go to a new page. If our variance equals 2, variance is 2, but the variance is also the mean squared deviation, that is not helpful to me because I'm dealing with something squared, and so what we can do is define the standard deviation. And the standard deviation, as the name implies, the standard meaning like the base or the average deviation, we're going to go from the square down to the regular by square rooting. So we're going to take the square root of the variance. So for us, the standard deviation, and I'll shorthand it like this, deviation is equal to the square root of 2, which is approximately 1.41. So looking at it like that, it makes a lot of sense because this standard deviation tells you how far away each observation is on average from the mean. So each observation is about 1.41 units away from the mean. And 2 is 1 unit, 1 is 2 units, so it's somewhere in between 1 and 2. Perfect, 1.41. Okay, so I want to talk a little bit about variance and standard deviation. We define variance, again, this formula for population variance, I should clarify that, population variance, as the sum of these squared deviations divided by the population total. And we define standard deviation to be the square root of that. So I'm not going to write the square root of that, but you get the idea. Standard deviation is equal to the square root of the variance. Okay, when we're dealing with population data, so you have a sequence of observations x, you have a sample size, a population total n. We write the variance. Well, let's first do this. Let me erase here. We write the mean with the Greek lowercase m, which is equal to the sum of the scores divided by capital N. We write the variance with the Greek lowercase s, sigma squared, and that's equal to the sum of these deviations squared divided by n. And we write the standard deviation with the just the sigma, not squared, but just sigma, and it's equal to the square root of the sum all over n. So these formulas are horrible to calculate with. They take a lot of time, and so we're going to develop a computational friendly version of these formulas in just a moment. If we were dealing with the sample data, we would have still the sequence of scores x, but we'd have a sample size lowercase n, and we would define the mean with this capital M, and it's equal to the sum of the scores over lowercase n. This is APA standard for mean. Standard deviation, we're going to write it with this SD, capital S, capital D, standard deviation. Sometimes we use the lowercase s, just regular s, okay, lowercase, but that's not APA style, so I'll use that from time to time if I slip up, but I always will try to write the way that we are expecting to write in publications, okay? So what we're working on right now is stuff for population. So if we could ease our computation, that would be great. Let's think about this a little bit. If we look at, let's change colors, the top part of the variance formula, so sigma squared is equal to this. The top part up here is called the sum of squares, shorthanded SS. Okay, sum of squares. If you expand that out and do a bit of algebra, you could show that the top part, the sum of squares, when you write it with as a squared deviation, the sum of the squared deviations, that's where the sum of squares come from, by the way, sum of squared deviations, we can actually write it like this: the sum of the x's squared. By the way, I'm referring to page 97, page 97, and down at the bottom it says computational formula. So we look at the sum of the x's squared minus the sum of the x's, all of that squared divided by the population, okay, total. This is a much easier formula. This right here is the computational formula. It's much cleaner and easier to compute. A lot of times calculators will already compute these values for you, whereas this method you'd have to sequentially do the subtraction and then square them and then add them up, and it's just a lot more time consuming. So from here on out, I'm going to use the computational formula just to ease our life, and I encourage you to do so as well. So we can define variance then. Sigma squared is equal to the sum of squares divided by the population total. Okay. One of the things to consider, this capital N is the population size. Most of the time we don't know the population size. Okay, which is kind of troublesome. So we're going to switch over to using sample variance and sample standard deviation and kind of look at what that means. So that's going to be another video post, but let's run through that example we've already done and recalculate the variance using this computational method, and then we'll come back and talk about sample standard deviation based on some nice theories. Okay, so let's revisit our example. We had our set of scores 1, 2, 2, 4, 4, and 5. Okay, and let's compute the variance directly. Let's skip over the mean just by using the sum of squares, that the computational formula for the sum of squares. Okay, so first thing we need the sum of the x's. So that's going to be 1 plus 2, on and so forth. And we did this computation already, we got 18. Okay, next thing we're going to do is square that. So the sum of those x's squared, which is 18 squared, and if I remember correctly, this is 324. I'm pretty sure. Double check that. I don't have a calculator with me. I'm trying to go from memory here. Okay, that's what us math nerds do. We memorize squares for fun. Anyway, the other thing we need, we don't, but it's okay. The other thing we need is the sum of the scores squared. Okay, so the difference between these, I'm going to first square and then add them up. So I have really 1 plus 4 plus 4 plus 16, 16, and 25. And what's nice about this, 16 and 4 is 20, so we have two of those, so 41, 46, 66. Alright, so the way the sum of squares is computed, again using the computational method, we have, maybe I'll sneak it in right here, we have SS is equal to the sum of the x's squared minus the sum x's squared over the sample size, this population size. So we get 66 minus 324 over 6. Right? Again, there's 6 scores, so that's 66 minus 54, which is 12. Alright, that is exactly the same that we got earlier when we looked at the sum of squares in this form. We also had 12, so it's good to verify that's the same. And so our variance here, sigma squared is equal to SS over n, so that is 12 over 6, so 2. In both cases, we got the variance of 2. And again, to find the standard deviation, we just divide. We just square root. Alright. In the next video, I want to take a look at sample standard deviation, sample variance, because that is a slightly different formula, and I want to highlight how you know which one to use, and kind of do some examples from the homework set in the end of chapter 4.